Hello. Last follow audible? Perfect. Nice. Yeah. So welcome to this. Thank you for taking out time on a Sunday and coming to hear us talk about few things. Um, I will be honest with you guys. The idea for this talk, like my talk, is like the way I've structured it is in a win-win situation, so that I learn something while preparing the material, and you, I don't know, like, in what year are you guys in? Most of you, first, second, third, third. Most of you are in third year. Yeah, that's good enough. CS branch, EC branch, IT branch.
Yes.
CS. How many of you are from EC branch? Okay, few of you. Yeah, so there's something for the EC branch folks as well. There's obviously things for the CS branch. Yeah, I hope you get inspired, like you get a direction from this talk. Right, so Rishiraj can introduce me. Yeah, I'm a machine learning engineer at Weights and Biases. I've been at this company for last 5 years, I would say. Yeah, it is one of the frontier company for all the ML ops related stuff. How many of you have heard the term ML ops? Right, so if you want to learn more about ML ops, you can check out Weights and Biases. Yeah, I'm also a GD, a Kaggle notebook master. I do a lot of open source contribution, and you can find a lot of my work at this URL, and I have some courses as well you can check out. You don't need to take pictures of the slides because I will have a QR code at the very end. You can just take it. And if you want to follow along, no. Like I will just share at the very end, right? So the agenda is kind of involved today. So we'll start with talking about CPU and GPU. Then we'll talk about a tool called arithmetic intensity. How many have heard this term? The CS folks, arithmetic intensity. None? I don't know. Like, should they have heard? So by third year? Should they have heard this term, arithmetic intensity by third year?
Yes.
Okay. Yeah, and then we'll talk about, how many of you have heard the word transformer? Right, how many have played with it, did something with it? Nice. How many of you feel, it can be any degree of confidence, but have some confidence about the architecture of transformer? Some, nice. That's good enough. So we'll talk about transformers slightly, and then KB cache and kernel fusion. So the basic idea here is that we want to understand how we can optimize any deep learning pipeline, any deep learning architecture, which is based off neural networks, and the case study for us is transformer. Okay. Right. So we will not go into the details of how transformer work stuff, but the way I have designed the whole material is so that it's like a journey where you start from low-level hardware perspective, go into like the tool that you require to understand what is to be optimized, and then finally few optimization techniques. And I have a ton of resources at the very end you can check out if you really want to dig deep into the content. Right. So first and foremost is what you want to optimize. How many of you have trained a neural network? Trained a simple image classifier. Okay, few of you. Right. So when you train a model, you have two things that you look at. You look at the train loss, which is the optimization that you want to reduce while you are training, and then when you are testing the model on an unseen data, you have some test loss or validation loss. So here you can see that the train loss is going down, but after a while the test loss kind of diverged, right? And that is reflected on the accuracy as well. The train accuracy is going up, like towards it's 90+%, but the test accuracy gets saturated somewhere around 70% mark. So knowing what is happening here will inform us how we can optimize, right? So the training loss is going low. So this is in the overfitting regime. Heard the term overfitting? Machine learning overfitting, a usual thing, right? So looking at this plot, we know that this is in the overfitting regime. So increasing the size of the model is not gonna fix this issue, right? So we know because it's in a certain regime, a certain solution is not the way forward. So to counter this, we might have to regularize, or we might have to increase the data set. There are, or do class balancing, etc. There are a way of tons of techniques that you can incorporate here. But the idea is that, like from a theoretical point of view, and all of these are like kind of empirical in nature, right? There's like, it's not like E equals mc squared, that there's a grounded theory. These are all experimentally deduced. So you need to just know, and you need to experiment it yourself to understand what's happening, and you can optimize based on that. And similarly here, in this plot, the train loss and the test loss are kind of similar. They are kind of are at the same level. So here, yeah. So since they are identical in nature, so regularization will not help here. So there's no point regularizing this model. So yeah. Just a quick summary from these two plots. On the trading side of things, when you know what exactly your regime is, you can optimize based off that signal, right? The same goes on the inference side. So when you have a trained model, you deploy that model on a system, and then you basically hit it with a request. So if it's an image classifier, for example, you will hit it with an image, and it will return you some prediction of that image. If it's a transformer, you have deployed the transformer on a GPU, and then you get, like you hit the GPU with some initial prompt. For example, write me a poem on something, and it will then generate poem for you. So what you are getting back, this whole scenario is what we call inference, right? We'll start off like so on a hardware level, or on an inference optimization. Like to understand inference optimization, we need to understand the hardware perspective, what's actually happening at the hardware level, because that will help us understand what we can optimize. So going forward, everything is going to be very involved. So if you're not understanding something, yeah, you can raise your hand, break me up, and I can maybe talk a bit deeper. But yeah, going forward, everything is going to be a bit involved. The idea is that you take away something that is inspirational, and you are curious enough to learn more about these topics. Right, so we'll start off with the CPU architecture. Can you see the screen, the folks sitting at the very back? It's fine? Yeah. So a CPU, you might have heard that CPUs usually have few cores, right? There are 8 cores in the CPU, or 14 cores, 16 cores, etc. So these cores are the computational unit in the CPU. Now, the cores in the CPU are kind of complex in nature. It is optimized, the CPU cores are optimized such that you can run many tasks as quickly as possible with the lowest latency possible, and mostly it's done in a sequential nature, right? So all the cores here will have something called L1 cache and L2 cache. So these caches are basically the memory here, which is embedded layer on the chip itself. So you do not have to read the data from the RAM, because reading data from the RAM takes longer time, because there's some wire and there's wire from the CPU to the RAM slot, and it takes time. So the whole thing, when we talk about hardware and especially memory, it's all about reducing the amount of time we are spending to access the memory, and that time is limited by a very important thing. Any guesses? There's a limit to which there's a limit till which we can approach this minimization of the time taken to access the memory. Yeah, so it's limited by the speed of light. So if current flows at the speed of light, if you elongate the wire between the memory and the computation unit, and if it's like if it's a light year long wire, it will take 1 year for you to access the data. A ballpark number, right? So we need to reduce that connection. That's why this particular L1, L2 cache memories are on the chip itself. So where the computation is happening exactly at that place, you have the connections to get the memory transfer, so it reduces it. So in these settings, like in this configuration, usually it's like some terabyte of data transfer per second that can happen. But because it's on the chip, you cannot have a lot of memory, right? So it has few cores. It is optimized for low latency and quick switching between tasks. So like that's what the CPUs have been designed for historically. So because it has low latency, it requires it cannot spend a lot of time accessing stuff from the memory. That's why it has some dedicated memories called cache. So L1 is on chip and it has a size of 16 to 128 KB. That's all. Some few kilobytes of memory is on this L1, and all the cores have their individual L1s. And L2 will have 256 KB to 1 MB per core, right? So these are few of the memory stuff that is there on the CPU to reduce the time. So if you program it well, you can do like quick computations and everything. So there's also something called L3. Modern computers do have that, and it's kind of a large memory. It has 2 MB to 32 MB of size, right? So if the data is not residing in the cache layer, so when an instruction is given to the core, it first checks if the data is in the cache layer, and if it's not, only then it goes to the DRAM to fetch the data. Right, so that was CPU. Now the GPUs, you might have used GPUs at some point for playing games or for training models, whatever. So GPUs do have, there are some similarities with the CPU, but GPUs have been designed for very specific tasks. So in CPUs, we have the concept of cores. We also have the concept of cores in GPU, but we usually combine few cores together and call it a streaming multiprocessor. So the combinations of different streaming multiprocessors constitute the GPU unit of your GPU, right? And this is done so that it can be very simple. It can be a very simple processor. All the cores just have one L1 cache, and it can just have some registers, have some L1 cache, and it can do some quick computations. That's all. So unlike CPU cores, these are very simple in nature. And these are all general purpose with small cache, as I said. Right, and there's also something called shared memory or SRAM. So in GPU, the L1 cache that all these streaming multiprocessors have, they are something that is controlled by the hardware itself on the hardware level, and there's also something called shared memory or SRAM in those chips, which can be managed by the programmer. So have you heard the term CUDA programming? Yeah, so CUDA programming is where you kind of can touch the SRAM level. Right, so again, in CPU, we execute one thread at a time, okay? But in GPUs, we compute thread blocks at a time, okay? And all of these are happening parallelly. So I will talk about what thread blocks are, but we have thread blocks. All these all the SMs or streaming multiprocessors get thread blocks, and they're all processed parallelly, hence increasing the computation time massively compared to CPUs. Right. So just give me a sec. Checking something. Yeah, so from a programmer's perspective, we have threads and thread blocks and kernel threads, but from a hardware perspective, it's a different ballgame altogether. So as I said, programmer's perspective, we have threads. So these are the smallest unit that has to be computed. we basically in a GPU configuration we basically group all the threads together to build this thread block. There's also a limitation on how many threads each thread block can hold, and all these thread blocks are executed by the streaming multiprocessor, which is the compute, a single compute unit in a GPU, right? As you can see, the thread is computed by the executed by the core. A collection of threads called thread block is executed by the streaming multiprocessor, and then we can group the thread blocks together, what we call a grid, and which is computed by the entire GPU, or collection of streaming multiprocessors, right? So, as I said, so streaming multiprocessor can handle thread blocks. Also, streaming multiprocessor can handle few thread blocks at a time, like 4 to 8 thread blocks at a time. These are all queued together. So one thread block is done, then from the queue it fetches the another thread block and executes that, just to increase the computation time. Yeah. So that's what is a programmer perspective. So you write your program such that, I mean, we usually do not, as programmers, we usually do not write at a level where we are actually trying to manipulate the threads itself. We kind of use something which is more abstract in nature, like PyTorch, to write stuff. But if you really want to gain optimization, you need to kind of understand these topics. And then if you are understanding this, you have something called CUDA programming. CUDA is a language that is designed by the NVIDIA for manipulating their hardware itself. Like, if you want to write really optimized code, you need to do CUDA programming. Again, that's not the topic of topic for this talk. It's a whole can of work itself. Alright, so the GPUs. So that was the programmer perspective. But on from the hardware perspective, and this image that you see here is a single streaming multiprocessor or streaming multiprocessor or SM for the GPU K20. So it's the K20 GPU's SM. So as you can see, there's some instruction issuing block there. There's some registers. So registers are unit memories that any chip will have. Those who have read about microprocessors, they will know what registers are. And then there's some shared memory. There's some read-only cache. There are some fancy stuff. Also, one important point: GPUs usually have multiple dedicated cores. So some of the cores are just dedicated for matrix multiplication, so that if an operation or instruction is to do matrix multiplication, it will do it far quicker than a regular core. Like we usually call this tensor cores. So each thread block is broken down into chunks of threads called warps. Again, I will just skim through it. The idea is that you have threads. Programmer perspective, you have thread blocks, which are a group of threads. But from a hardware perspective, when an SM gets a thread block, it then divides the thread blocks into something called warps. Warps are basically groups or groups of threads, and it's usually 32 threads in a single warp. And you can also say from a hardware perspective that a group of warps will constitute a thread block, right? Because a thread block is divided into warps. Again, weird stuff, but instructions are issued on the warp level. So all the threads that will get the same instruction, so all the warps will get the same instruction. That's why all the instructions are issued on the warp level, and then execution is done using this execution mode called single instruction multiple threads. I don't know if you have read about SIE, SIMT, SIMD, etc. But the idea is that once a warp gets an instruction, the instructions are then executed in this setting, single instruction multi-thread, because there are multiple threads in that warp. These are all fancy things just so that you can optimize the performance. Or you cannot, the folks who are building the hardware can optimize the performance, right? And then within the warp, because all the individual threads will have instruction, they all execute in the single instruction multiple data mode, so that all the threads can fetch multiple data points just to do the computation quickly, right? And then if you go even deeper, there's something called warp schedulers. There's memory schedulers, etc., etc. So we can go down the rabbit hole, but that's not the is pointless at this point, because just the fundamental understanding that as a programmer you can use CUDA to and have a perspective of how to write a program. On a hardware level, something else is happening. That's the differentiation I just wanted to show. Right. So if you talk in a multi GPU setting, just to switch back. As I said, if you see the diagram there, as you can see, there are multiple SMs in a single GPU, and all the SMs will be getting some data from the L2 cache, and there's also device RAM. So when you hear that the GPU have 8 GB or 80 GB or 40 GB of DRAM, it is this device RAM. So it's not this is not the system or a CPU RAM that we know, 8 GB of RAM, 16 GB of RAM. It's dedicated DRAM which is attached at the same level where the chips are situated, so that the reading time is as minimum as possible. Imagine that the DRAM is on the motherboard and the chips are someplace else, and there's a wire. It will take more time to fetch that memory. So the device RAM or the GPU RAM is exactly where all the compute units are. So it's very close by. So the data is basic. So when you do NVIDIA SMI on a collab notebook or on a system, you basically get the value of device DRAM. So the data is initially stored in the device DRAM. When you load a model, the model weights are loaded in device DRAM, and then a single SM reads that data from the device DRAM via L2, and it basically speeds up the whole memory access stuff. And then if you have multiple GPUs, all of those GPUs talk together with something called NVLink. It's a fancy thing. It's a fancy data transfer mechanism. And usually in a single node there are 8 GPUs that you can find connected together in NVLink, right? And then finally, and I promise this is the final bit for the hardware thingy. And finally we have all this, a node or a single GPU talks to your SSD, or hard disk, or your network interface, or your system DRAM, or the RAM in your motherboard that's installed on your motherboard. It talks via something called PCIe. It's basically called peripheral. So PCIe and SXM, these are two form factors in which the GPUs have a communication with your system DRAM or your network interface, etc. Right? So, just to summarize, we have some compute unit in a GPU called SMs. The compute unit needs to have the data as well to do the computation on. The data is ideally stored in the device DRAM, and all the SMs obviously will not throw all the data to the compute unit, right? The data is broken down into chunks, and all the chunks are first loaded in an L2 cache, which is a bigger memory on the chip itself, or closer to the chip itself, and from the L2 all the L1s or SRAMs will fetch the required data, right? All of these things are hidden away from us as a programmer, as a machine learning engineer, as a machine learning practitioner. These are all hidden away from us. But knowing something about it is always beneficial, especially if you are willing to do inference optimization. Right. So this is the data card for NVIDIA A100. All the 40 GB, 80 GB configuration, and then you can see like 40 GB and there are two different form factors, PCIe and XSM, right? And the only difference here is that the XSM will have higher memory bandwidth of 2039 gigabytes per second, where your PCIe can have a max bandwidth of 1935 GB per second. Anyway, the point here is that we measure the computing capability of a GPU with something called flops. So flops is floating point operation. You must have heard this term, flops. So floating point operation is number of operations it can do in a single second. So that's what that determines the compute capability of the GPU. And then as if you can see here, TensorFlow 32, TF32 or bfloat 16. So it has a terabyte flops of 312 in a float 16 precision. So you have float 32, float 16, etc. So in float 16 precision, you have 312 teraflops, and that is matrix multiplication. But if you are not doing matrix multiplication in a GPU, you only get 19.5 teraflops. So the difference in a matrix operation, mathematical operation, and a non-mathematical operation is huge. Again, just to reiterate, if you are doing matrix multiplication on 800 GPU, you get 312 teraflops in a float 16 precision. And if you are doing the same, and if you are not doing matrix multiplication, you're like doing some addition, subtraction, etc., you only get max teraflops of 19.5. Huge difference, right? Yeah. Now, so from here, what is important to like kind of understand is if like your neural network architectures should be designed such a way that it does a lot of matrix multiplication and not unit computation like element wise computation like adding some values together or dividing or normalizing some values together. Instead, do as much matrix multiplication as possible. That will speed up your that will take the most benefit out of your GPUs. Yeah. Yeah, so matrix multiplication is favored. Also, where you are keeping the data is also very important. Guys, are you with me, or is there any question, something confused? I understand this is a very involved topic. Might not be straightforward to realize, but I hope you get something out of it, right? So, getting back, matrix multiplication is favored if you are using GPUs, but it's also important where you are keeping your data. And let's try to understand this from this like simple mental model. So if you are reading the data from L1 cache, it only takes it takes X nanosecond. But when you are reading it from L2 cache, it is gonna be taking 2 to 3 times that of L1. If you are reading the data from HBM memory or the device DRAM or the GPU RAM, it's gonna take 10x the time. When you are reading it, like when you're sharing the data between different GPUs, it's gonna take 50 to 60x the time that it takes to read from L1 cache. And then finally, if you are to load the data from the CPU to the DRAM, the device DRAM, it's gonna take somewhere close to 300 times that one L1 cache, right? So if you keep your data in your CPU and then you send it to the GPU, it's gonna take 300 times that if your data is situated in L1 cache. And even if it's situated in the device, the GPU device itself, the difference is 30 times, or like 30, yeah, there's a difference of 30 factors here between the device DRAM and that of the CPU if you're reading the data from that, right? So that's why if you use PyTorch, we do something like data dot to device, and the device there is GPU. So we send the data to the GPU so that the reading time from the GPU is as minimum as possible. Right. So yeah. So final point, flops matter. So when you're looking at GPU, it does matter how much flops it has, but it also matters when you're writing your neural network, like when you're writing your deep learning pipeline, where your data is situated. So that's also equally important. Yeah, so based off that, your deep learning pipeline is gonna be the efficiency of it can be modeled in 3 ways. One is compute bound. So the time that you are spending, or the time that your GPU is spending doing actual computation. So if you have enough things to compute, then your system will be compute bound because it's not spending a lot of time reading the data, but rather doing the computation. So the flops, the peak flops of the GPU will matter. So at that point, all you can do is buy more GPUs and use that to increase the compute. Yeah. Now, if you are not, if you're spending most of your time, or the GPU is spending most of the time getting data from the DRAM, the GPU DRAM, or from CPU, it's in the memory bound regime. And finally, there's something called overhead bound. So all the time that the GPU is spending not reading the data and not computing anything of that data, that's the overhead. So overhead can be Python interpreter, it's damn slow. Like if you're all the time that your PyTorch, TensorFlow, Keras frameworks will take, that's the overhead. So there are different overheads that happens. Like if you when the CUDA kernels are launched, that's also an overhead. So all of these time together kind of adds up to show the total time that it requires to train your model or to do inference on your model, right? Yeah. So we need to model this. So we need to have a tool using which we can kind of have an insight into a component of your deep learning system. It might be the data pipeline. It can be your architecture itself, as to which regime of computation of efficiency it is in. Because if we don't know that, it is going to be very hard to pick an optimization strategy that can be useful. Alright, so let's imagine a very simple model where we have a function which reads from the memory, then it performs a math operation on that data, and then it writes back to the memory, right? So it reads the unit data, it does some computation, and then it writes back to the memory. That's a very simplified model. So the time spent will be so what the time is gonna be the memory time. So the time that it requires to access from the memory, then it will be the time that is required to do the computation, right? So as you can see, there are two there's a read time and there's a write time. So together they will form the memory time, because that's the read time spent, and the performance math operation is your compute time. Right, so assume that your memory time and your compute time are overlapping. So like the moment, so like your GPU is saturated, so the moment it's reading some data, at the same time it's doing the computation. So if that's the case, and all of this modeling is going to be happening there when your GPU is saturated, so it has all the data that it can have, and it's doing the computation at maximum, then we can calculate that the total time is going to be based off what of the two, the memory time and the compute time, is the maximum, right? So if your system is spending a lot of time reading from the memory, then the total time that is going to be that's going to take for inference is going to be T memory or memory time, right? So if your system is compute limited, it's going to be T compute is going to be greater than T memory, and vice versa, right? So we can calculate this. So we can calculate this memory time and the computation time. So the memory time formula is given by the number of bytes that can be read or that is being accessed divided by the memory bandwidth, and the computation time is number of operations that's happening divided by the compute bandwidth. So the memory bandwidth is, if you remember the data or the screenshot of the NVIDIA A100 GPU, there the memory bandwidth was something 1939 gigabytes per second, and compute bandwidth was 312 terabyte flops. So these are like constant values that you get from the manufacturers, and as per depending on your algorithm, depending on the computation that you are doing, it will have different read time, or the time spent to read the data from the memory, as well as the time taken to do the operations. Right. So if a system is compute bound, that means the time that is being taken to do the computation is more than that of memory. Like we can do this simple calculation here, like ops by compute bandwidth is greater than bytes by memory bandwidth, etc., and we can just arrange everything. So when we do the arrangement here, what you see here is that ops by bytes. Now this term the time taken to do the operation divided by the time taken to read the data from the memory is called arithmetic intensity. And the memory and the compute bandwidth of your GPU divided by the memory bandwidth of your GPU is called ops byte ratio, right? So just to conclude, if your arithmetic intensity is greater than your ops byte ratio, then your pipeline is compute bound. But if your ops byte ratio is greater than your arithmetic intensity, then it is on the memory bound. That is memory bound, right? And this ops byte is something that is fixed. It's dependent on the device specification that you are using. Just like let me try to explain this with an example. Now this is the data chart for a V100 GPU. It can have a maximum flops of teraflops of 125 in floor 16 precision, and it has a bandwidth of 900 gigabytes per second. So it can transfer 900 gigabyte in 1 second. That's a lot. So we have this GPU. So the compute bandwidth here is 125 teraflops. The memory bandwidth here is 900 GB per second, which is off chip, right? This is the time taken to read from the device DRAM itself or the GPU RAM itself. But if you are reading it from the L1 cache, it's 1134 gigabytes per second. But yeah, we'll take the 900 one for here. So the ops byte for a V100 is gonna be 139. So the ratio is like we divide 125 flops divided by 900 bytes per second, like we with the 10 to the power 9 to the power 12, we get 139 ops per byte, right? I don't know if you can see this chart here, but this is something you can find on the NVIDIA website. Point is, let me just read it out. The linear layer or the layer which is doing fully connected operation is just taking 312 flops per second. So 312 is greater than 139. That's why matrix multiplication on your fully connected is compute bound, whereas doing normalization, doing max pulling, doing ReLU activation, etc. are all like less than 10 flops per second. So all of those are way lower than the 139 ops byte ratio. That's why all of these operations are in the memory compute region, right? So knowing where different layers of your application are, different layers of your architecture are, like in what regime, you can optimize them accordingly. And just one quick caveat here. So these are both linear layer, but you can see that in one time, like these are both the linear layer or the fully connected layer, but here it is compute bound, but in the second one it is memory bound. The reason is that the second one is doing the inference with just one batch size. So the batch size, the amount of data you are processing at the time also kind of takes you to different memory regimes. So so with one batch size in this example, it was only taking 1 flops per byte, which is very small. So you can have a data, you can to speed it up or to bring this to the compute regime, you have to have a batch size of at least 256 or 128. Like close to 128, it will be close to the compute bound. So if your layer or if your architecture is compute bound, then adding in more GPUs makes sense. But if your architecture is memory bound, then adding in more GPUs will not do any good. Rather, you need to optimize where your data is situated. Right. So all the deep learning architectures can be broken down into 3 core operations. So there's something called element-wise operations. So the layer in this category will perform some operation on individual elements independent of each other, right? For example, ReLU. So anyone knows the formula of ReLU? No. So ReLU is basically max of 0 and that number. So if that number is greater than 0, then it will be that number. If it's less than 0, it will be 0. It's a simple comparison. So it is done on individual elements. So that's why it is called element fetch operation, and usually this is memory bound. The second operation is reduction operation. So reduction operation is basically an operation that is done on a collection of values together. Some examples can be pooling layer. So if you have created a convolution neural network wherein you have max pooling, it will be a reduction based operation, and non-reduction layers are reduction based, softmax is a reduction operation, etc. And finally, there's something called dot product operation. So the fully connected network, the fully connected layer or linear layer is doing a lot of matrix multiplication. So all the layers that is doing heavy matmul or matrix multiplication are doing dot product operations, and all these GPUs are optimized for dot product operations, and they are not optimized for element wise and reduction operations. So in your architecture, if you can reduce the number of pooling layers or softmax or activation layers, I mean this is very tricky, it's not that easy to do, but if you can have, if most of your architecture is doing matrix multiplication, then it's going to be leveraging GPUs the best. Alright, so the point here is that depending on your architecture, you can even choose what kind of system that architecture requires. And yeah, so that was core operations. Then let's go into this nice yeah. Now it's gonna be fun from here, I promise. Yeah, so yeah, can you see the screen here? I don't know how good it's been. Yeah, can someone help with the lights?
लाइट को
Is it better? Yeah, so this is a really nice website that you can check out, Transformer Explainer. Here we have a simple transformer which I will run and show you what exactly happens from an operations point of view within a transformer. Right, so we are doing, like, we have the input here like this. Data visualization empowers users to analyze, and then when we hit generate, it basically sends this string or this data to the transformer, and the transformer, I mean, yeah, I don't know if you know the architecture, but it is doing some fancy computation within, and the most important computation that I want to talk about is the multi-head self-attention. And once you have the computation done, like multiple times, there are like 11 identical blocks. So like this computation is happening 11 times, you get a probability, like you get some value for like in your vocabulary, the user is being predicted here, the word user. So this word user is again added to the prompt. Data visualization empowers user to analyze user. Okay, it's a bad one. We can change the temperature, analyze, yeah, data, and then when we hit generate again, it will bring the data here which was predicted before. It does the computation again, and the next prediction is AND. So with AND here, I can hit generate again, and then it does the computation, and it again gives a score to yeah, to find. There should be a word to find here. It's not showing. Or make, whatever. Yeah. So the point is, you start with some initial data or some priors. You give it to the transformer network. The transformer network performs some computation, and then it gives a prediction or the next word or the next token, right? So that's all that happens within a transformer. So this is called, so technically, like, or formally, this is called auto-regressive generation. So you start with some priors and then you generate one token at a time, one token at a time. So on the data side, what happens is all these particular strings, data, visualization, M, powers, etc., these are all converted to numbers. So data is converted to this number 6601. Visualization is converted to this number 32704. These are all the token IDs. and yeah, so this number is then embedded into a vector of size 768. It is then added with another vector called positional encoding of vector of size 768, and then you get this final vector. So token embedding plus positional encoding, you add together and you get a vector of 768. So this data, this word data, is been represented by a vector of size 768. That's the first bit in transformer. Yeah, once this is done, you compute this attention value, and then based on the attention value, you get some. You basically assign some values back to the data. So if I show here, the data here had a size of 768, and the data here also has the size of 768, right? So some computation happened here, which basically converted the values that were initially given to this data representation into a new, like this vector 768 is not the same as this vector 768 here, right? And what's happening here is that, is doing this self-attention, is doing this self-attention computation, wherein there are QKV, like these are query, key, and value matrices that I'm just talking in an inference setting. I'm not talking in a training setting. So all these matrices here that you see, these are all learned matrices. The value that we saw here as well, data to 768, this token embedding and everything, these are all learned embedding. So there's an operation that's happening which is converting the data to 768 vectors, right? And positional encoding is also learned. Everything is learned here. Similarly, when we have the QKV computation, the query, key, and value are learned. So you give the data, we basically multiply the vector of the data with the matrices here. We get some values, the QKV values on this side. I don't know, like, this is very tricky to explain without pen and paper, but yeah, this is what 768 vector dimensional. This matrix is 768, 2304. So 768 matrix multiplication with 768 2304 will give me a vector of size 2304, which is here, right? And we get the same for like a vector of size, like a similar vector of that size for the Q, for the K, for the V, because we have Q matrix here, K matrix here, and V matrix here, right? So this is the self-attention that's happening. So when this is done, you basically create a new vector that is representing the data, and it's called key, and then you have some representation as query, and then some representation as value, and then you do this fancy simple like dot product with the query and the key, which gives you some value, and then there's some masking that happens, like we can ignore that, and then we do some softmax, which is gonna like give more significance to some value. So you can see data query and data key have a correlation of 1 because they are the same thing, but data and visualization have a correlation of 0.84. So basically what's happening is all the values are being attended to based on what it has seen in the past. If you remember, AND is something that we predicted, and there was some compliance, and we can see how it is correlated with the previous matrix and everything. And once this attention is done, this computation is done, you basically get back like the attended logics for all the different tokens, and you do it multiple times, and at the end you basically get a prediction of what word is to be given back automatically here, appended, and then you can generate again, create a new word, and so on and so forth. So you can imagine that when you are doing this, the QKV matrix or this value here, QKV value. So if you have noticed, last time it was 9,2304. Now this is 10,2304. So because we predicted added one more token, we had like this value increased here. Inform was predicted. Let's hit generate again, and you will see that the value might be 11,2304. So you can see that this particular matrix QKB is increasing as you are increasing the number of tokens that is being generated. And you can imagine that this matrix is gonna be living in your GPU itself. So the more the tokens you predict, the more GPU is gonna be taking, and the bigger the matrix size, because the matrix here is also increasing 11,768. The bigger the matrix here, that multiplication is gonna take longer time, which will give more value. So the GPU consumption will increase as you are generating new tokens. The amount of time that is going to be invested to do that computation is also increased because this is increasing. Right? I hope you get the point that when you generate tokens, the more the tokens you generate, the more memory it requires and the more time it takes. Yeah, let's get back. So that was transformer. Again, this talk is not about transformer. It can take 5-10 hours just to talk about transformer. It's that nuanced. And I would hardly suggest that you check out Andres Karpathy's YouTube channel to learn more about transformers, right? So on a high level, like we can then optimize the architecture on two levels: on a high level algorithmically, and on a low level, like on the hardware level. So when you're doing the inference, so there's something called prefill stage. As you see here, all the data that was first given as a prior, it then does all the computation, and it then creates this tensor or this matrix 11,234. So imagine this was the input. It created this matrix. So this particular stage, when you are generating the QKB matrix, this is the prefill stage. Okay. So once you have the prefill, this is where all the hidden representations are computed. Then you start decoding one token at a time, and I showed already that as you are computing more token, this matrix is increasing. Like it was 10,768, it's now 11,768, and then the QKB also increased from 10,2304 to 11,236. So this is increasing as you're generating more token in a auto regressive decoding step, right? Yeah. So this is a nice gif I found somewhere, which is basically showing the same thing. As you increase the number of queries or number of tokens, you are basically increasing the size here, right? And every time, and in a naive transformer implementation, you are basically doing this Q cross K transformer, or the dot product of Q and K every time you have a new token generated, which doesn't make any sense, right? Because the query representation and the key the key representation is not gonna change if you add a new query to the queue, and hence we have something called KV cache. So when you are doing it without caching, and actually like it's better to show this. Like the insight here is that when you are decoding in a like auto regressive decode, when you're doing that, we do not need to recalculate the previous token attention, right? Once we have computed that, there's no need to compute it again, because that is one thing that is not changing. All we now need to do is compute the attention for the new token and how all the previous like words or the tokens are going to be impacting the generation of the new token. That's all we want to compute. So without cache, we are computing this QKT, like this matrix again and again and again. But if we can cache the K value and the V value, then all you need to do when you have a new token, all you need to do is compute the last value, the last key value and the last value token. Right? That's all you need to compute, and then you can go ahead from there. So when you hear the word caching, it means that you are keeping this particular matrix that have been recomputed or that have been computed already into a memory. So that's where some of the issues of KV cache happens. So I hope you get the point that KV cache is all about you compute it once and then you keep it in a memory instead of recomputing again and again and again. This just gives you a lot of computational gain off the shelf. But again, there are caveats to it, and I will just run through it quickly. So we were able to reduce the number of operations from by a factor of L, because like when we are generating L tokens, the L minus 1 were already computed for you, so you do not need to account for that. So you reduce that, But because you are then saving it in memory, you are not effectively minimizing the amount of time that is gonna be spent accessing the memory. So if I just reiterate, your vanilla transformer architecture was compute bound, right? But when you used this simple trick of KV caching, you move the architecture to being memory bound, right? Because now the memory is the bottleneck here, right? So the optimization happened with KV cache itself, but because of that optimization, something new happened, which is took that architecture to being memory bound. So you need to do some optimization in that domain, in that regime, right? And another issue is that the KV cache will grow as a sequencer. You can imagine, right? I showed from 10, 2304 it went to 11, 2304. So as you increase the number of tokens, the cache is going to increase, which will in turn increase the memory that is going to be consumed on the GPU. So your GPU is anyway keeping the model parameters itself. So like if there's 80 GB in your memory or in your GPU, and you have a big model that's loaded up, it's already taking up most of the space. So if you start saving the KV cache values as well, the same GPU is gonna eat up the GPU real estate that you had for the memory. For loading the parameters. So these are few of the issues. So one way to take it away from the memory boundedness is to batch number of requests as much as possible. So imagine you have a 810 GPU and you have a Llama 7 billion model. So that 7 billion model will take 14 GB of memory in your GPU, and GPU had the 24 GB of memory real estate. So only 10 GB is left because 14 GB is used to load the model, right? And now if you compute the amount of tokens or like compute the size of the KV cache, I mean you can go through this formula yourself. You can at max store the computed KV value for 19,230 tokens. That's all. And because our sequence length, the maximum sequence length that the architecture can handle is only 4096, we can basically do 4 batches at a single time. So you can compute 4 batches at a single time, and this will allow you to get the maximum out of your GPU. Right? So batching helps if you are doing KV caching, right? And then another thing that you can do is, because as you are increasing the KV cache, the amount of storage is also increasing. So one trick there is to basically quantize the KV cache itself, and this is a nice chart I found from a Hugging Face blog. The only point I want to show here is that just like the line that you see here, the int4 quantum, this is the quantization technique of KV values. This is very much similar to the F16. So when you save the KV cache in full precision of float 16, the performance that you get there versus the performance that you get when you quantize that to int4 is more or less the same. So you are able to reduce from float 16 to int4, and it saves a lot of memory. So quantization is another technique that you can do, right? And then after this, there are many more topics like multi-query, attention, group attention, prefill with chunking, sliding window attention, etc., etc. Like the list will go on. So when we just quickly talk about hardware level optimization, right? So this is the SM for NVIDIA 800 GPU. There are 108 SMs in that GPU. And yeah, they're like all the stats that you can check out. The only point is that if you can break large matrices into smaller chunks, because it has a good 192 KB of L1 cache, it's good memory. You can do a lot of computations. But this is not the case for MATML operations. I don't know if you can see this. This is from a paper. It's laying there. But the interesting bit is that 99% of the flops of your system, 99.8% of the flops is taking 61% of the runtime of your GPU, but your normalization layer and your element-wise layer like sigmoid, like 10, etc., is only consuming 0.2% of the total flops, but it's taking 39% of the runtime. So it's just 0.2 computation, but taking the most of the time. Hence, saying that okay, whatever operation was used to do this to come up with this number is hugely memory bound because it's taking a lot of time just to do some simple computations. So what you can do there is that, so if you are reading some data from the memory and then you're doing some computation, instead of writing it back to the memory and then reading it again, writing it back and reading it again, what you can do is, you can basically, okay, this is an example of softmax. I can just skip through it. But the idea is that in a softmax, you are doing the exponential of some tensor, and then you are also adding up the exponential of all the other tensors, and then you are dividing that together. So it takes it takes a total memory of 5L squared plus 2L. That's the total memory that it takes, or a total time that it takes to do the read and write on the memory. But if you can fuse the operations together, that means if you can do the addition, if you can do the exponential and division in a single instruction, you only have to then read once and then write once. So by doing that, you can increase the amount of speed by 2.5% or 2.5x that of a nice softmax. And these are sort of things that if you use a transformer, you will get out of the box. But just a point, XLA compiler in JAX is something that you can check out if you want to learn more about this. And if you really want to write your own fused recorders, like optimize your performance, you can use something called Triton or Alas. Yeah, and there are a lot of interesting topics in this domain as well. Finally, you can check out all the resources. These are just links here. If you want to read more, learn more, you can check them out. Yeah, now if you are interested, you can just scan this so that you have the slides that you can check out, and that's it. Just to summarize, you need to understand where your computation, where your architecture is on an efficiency level. So is it compute bound or is it memory bound? And once you have that understanding, then you can pick different optimization techniques to fix that. So if you use KV cache, you will take the transformer from compute bound regime to memory bound regime, but you can do batching to reduce the effect of reads write that happens. And then kernel fusion is another technique that you can use to speed up. You take the operations from being memory bound to compute bound, right? I hope you found it insightful. I know it was involved. If you got bored, I'm sorry for that, but I hope it was insightful. Yeah. Thank you, and if you have questions, you can check me out on Twitter and you can ask me. Done.